In this video, I will show you how to set up and evaluate an integral that gives the volume of a solid formed by revolving a region about a line. In the case of problem number 4, we are revolving the region around the x-axis. If I take this blue region and I rotate it around the x-axis, it forms this kind of bowl shape. Now imagine that the bowl is solid and not hollow. Our job is to find the volume of this solid. Ultimately, we will calculate the volume of the solid by slicing the solid up into many disks like this one. I'm going to break this up into a 3-step process. Step 1 is to find an expression for the radius of a single disk. Step 2 is to find an expression for the area of a single disk, which of course will be pi r squared. And then step 3 is to find the volume by integrating the area. When you integrate the area, you are adding up all of these disks in order to form the volume of the solid. So step 1 is to find an expression for the radius. But this curve is formed by the function square root of 9 minus x squared. So the length of the radius will just be the value of the function. In other words, the length of the radius will just be the square root of 9 minus x squared. In general, when the radius is vertical like this, an expression for the radius will just be the top function minus the line that we are rotating around. But in this case, the line is the x-axis. The line is 0. So if we just do the top function minus 0, it's really just the top function. Step 2 is to come up with an expression for the area of a single disk. The area of a circle is always pi r squared. And right now, we are looking at an expression for the radius. So to turn this into an expression for area, we need to take our radius and turn it into pi r squared. So if I put a pi in front of this, and then I square it, now this is an expression for the area. The last step is to form an expression for the volume by integrating the area. So I can just take my expression for the area and integrate. In this case, the disks will be stacked up from left to right. So we are integrating with respect to x, and the limits of integration will be from 0 to 3, because the disks are stacked up from left to right, 0 to 3. Before we evaluate this integral, I would like to simplify it a little bit. We happen to have a square root that's being squared, so the radical and the squarage will cancel each other out. Also, I'm going to take the pi, this constant, and put it out in the front. So we end up with this. We can integrate term by term. The antiderivative of 9 is 9x. And then I have the next term, x, we increase the exponent to 3, and we divide by the new exponent, so we have minus 1/3. Then we apply the limits of integration from 0 to 3, and don't forget about the pi that's out in the front. So we need to find the value at 3 minus the value at 0. I'm leaving the pi way out in the front, and then here's the value at 3 minus the value at 0. Of course, all of these 0 terms will disappear on the next step. If this was a free response question on an exam, you could just leave your answer just like this, full credit. However, when you're practicing, you should always simplify because you want to prepare for the possibility of a multiple choice question. The expression simplifies down to this, which is equal to 18 pi. So the volume of this solid of revolution is 18 pi. For problem number 8, we will do something very similar, but this time we will find the volume of the solid generated when we rotate this blue region around the y-axis. If you rotate this region around the y-axis, you get this upside-down bowl shape. We can calculate the volume of the solid by analyzing a single slice, which is a disk. Notice that these disks are stacked vertically, which means that ultimately we will find the volume by integrating with respect to y. For that reason, we need to rewrite the function in terms of y. So let's take the original equation and solve for x. If we square both sides of the equation, we get y squared is equal to 16 minus x squared. Next, if we add x squared to both sides of the equation and subtract y squared from both sides, we get x squared is equal to 16 minus y squared. Finally, if we take the square root of both sides, we end up with x is equal to the square root of 16 minus y squared. Normally, I would say plus or minus, but we are strictly in the first quadrant, so we only need the positive version. Now it's time for the three-step process. Step 1 is to find an expression for the radius of a single disk. Well, the length of this radius will just be the x-coordinate of the function, and we just found that x is equal to the square root of 16 minus y squared. So, the square root of 16 minus y squared is an expression for the radius. When we get to problems that are more complex, we will sometimes have to find an expression for the radius by subtracting the function on the right minus the line. But in this case, the line was just the y-axis, so the line was 0. So we just ended up with the function on the right. Step 2 is to come up with an expression for the area of a single disk. Area is pi r squared. Since we have an expression for the radius, all we have to do is square it and put pi in front. The final step is to write an expression for the volume by integrating the area. So here is our area expression, so we can just integrate. I think I will automatically leave the pi out front. It's just a matter of what are the limits of integration. Remember, these disks are stacked vertically. That's why we are integrating with respect to y. So these disks are stacked from 0 to 4. So those are the limits of integration. As before, the square root and the exponent cancel each other out, and we are just left with 16 minus y squared. Integrating term by term, the antiderivative of 16 is 16y, and then for the next term, we increase the exponent by 1, and then we divide by the new exponent. So we have this. We apply the limits of integration from 0 to 4. So therefore, we need to find the value at 4 minus the value at 0. So I'm leaving the pi out in the front, and then inside the parentheses, we have the value at 4 minus the value at 0. Again, if this was an exam, this would be an acceptable answer for a free response question. But let's keep going to prepare for a potential multiple choice question. These 0 terms will disappear on the next step. Simplifying a little bit, we have this. Making like denominators, we have this. And subtracting those fractions gives us this. So the volume of the solid of revolution is 128 pi over 3. For the remaining problems, we will have to draw the graphs ourselves. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the line y equals 4. Calculus requires us to know what all of the parent functions look like. So for example, we know that y equals x to the third power basically looks like this. Putting a 1/2 in front of it just flattens that out a little bit. The line y equals 4 is a horizontal line at 4. Of course, the line x equals 0 is just the y-axis. So this blue region is the area bounded by the three functions. If we rotate this region around the line y equals 4, we get this bowl shape facing towards the left. As before, we can calculate the volume of this solid by analyzing one disc-shaped slice of the solid. Step 1 is to come up with an expression for the radius of a single disk, and in this case, we will be careful to find that expression by subtracting the top function minus the bottom function, which in this case is just 4 minus 1/2 x to the third power. So here is our expression for the radius, 4 minus 1/2 x cubed. Step 2 is to come up with an expression for the area of a single disk, but the area is always pi times the radius squared. So we can just take our expression for the radius and square it and put a pi out in the front. Finally, we can form an expression for the volume by integrating the area. We notice that the disks are stacked up from left to right. That's why we will integrate with respect to x. So we will take our expression for area and integrate. I like to leave the pi out in the front. What are the limits of integration? Well, this is going to take a little bit of calculation and thought. From left to right, we know that the disks are starting at 0, but how far to the right do they go? That's going to be the x-coordinate of the intersection between the red curve and the purple line. So let's set these equal to each other and solve. Setting the two equations equal to each other, we have 1/2 x to the third power equals 4. Multiplying both sides by 2, we have x to the third power is equal to 8. Taking the cube root of both sides, we get x is equal to 2. So this is the x-coordinate of the intersection between the two curves. So that tells us that the second limit of integration is going to be 2. The disks are stacked up from left to right, 0 to 2. So it's time to find the volume by integrating this expression. However, U substitution wouldn't really work on this problem, so how do I integrate it? We need to come off to the side and expand this expression. So I'm going to do 4 minus 1/2 x to the third power times 4 minus 1/2 x to the third power. Distributing the 4 gives me 16 minus 2x to the third power. Distributing negative 1/2 x to the third power gives me negative 2x to the third power plus 1/4 x to the sixth power. And combining these like terms gives me 16 minus 4x to the third power plus 1/4 x to the sixth power. Let's substitute this back into the integral. So now we have this. Let's integrate term by term. I'm going to leave the pi out in the front of parentheses, and then the 16 antiderivative is 16x. Moving on to the x to the third power, I'm going to increase the power by 1, dividing by the new exponent. 4 divided by 4 is 1, so they cancel each other out. Moving on to the third term, I see that x to the sixth power. It will become x to the seventh power. When you divide 1/4 by 7, you get 1 over 28. So I'm going to have plus 1 over 28. Applying the limits of integration from 0 to 2 tells us that we need to find the value at 2 minus the value at 0. Leaving pi outside the parentheses, I have the value at 2 minus the value at 0. Obviously, every term has an x in it, so the value at 0 is just 0. Applying the exponents gives us this. Performing the multiplication gives us this. Making like denominators gives us this. And combining like terms gives us this. So the volume of the solid of revolution is 144 pi over 7. And this is what you would see as an option on a multiple choice question. But if it's a free response question, you can leave it at any of these steps. For number 22, let's find the volume of the solid generated by revolving the region bounded by the graphs of the 4 equations shown about the line x equals 5. We need to sketch the 4 functions, starting with xy equals 3. Isolating the y, we get y is equal to 3 over x. Let's compare with the parent function, which is y equals 1 over x. We should have memorized a long time ago that this parent function has a branch in the lower left quadrant and a branch in the upper right quadrant, approaching the x-axis and the y-axis asymptotically. Y equals 3 over x is just 3 times 1 over x, which is a vertical stretch by a factor of 3, but that does not change the overall shape of the graph. Y equals 1 is a horizontal line at 1. Y equals 4 is a horizontal line at 4. And x equals 5 is a vertical line at 5. The region bounded by the 4 equations is now shown in yellow. If we rotate the yellow region around the line x equals 5, we get this sort of flat bottom bowl shape. We can calculate the volume of the solid by analyzing one slice of the solid, which is a disk. Step 1 of our 3-step process is to find an expression for the radius of a single disk. When the radius goes from left to right, you can find an expression for the radius by subtracting the right side minus the left side. In this case, the right-hand side of the radius is 5. And the left-hand side is the red function xy equals 3. Well, we need to either write this in terms of x or in terms of y. Which one is it going to be? Let's think ahead to the final step where we integrate. Notice that these disks are stacked vertically. That means we are going to end up integrating with respect to y. For that reason, we need to write the red equation in terms of y. So, dividing both sides by y, we get x is equal to 3 over y. So, back to our expression for the radius. We were doing right minus left. So that was 5. Now we're going to say minus 3 over y. Cool, we have our expression for the radius. Step 2 is to find an expression for the area of a single disk, which is always pi r squared. So since this is an expression for the radius, to turn it into an expression for the area, all we need to do is square it and put a pi out in the front. Step 3 is to find an expression for the volume by integrating the area. So we will simply take our expression for the area and integrate. For the limits of integration, notice that the disks are stacked vertically between 1 and 4. So these are the limits of integration. In order to integrate this, we need to expand this binomial. Let's do that off to the side. 5 minus 3 over y squared is the same as 5 minus 3 over y times 5 minus 3 over y. Distributing the 5 gives us 25 minus 15 over y. Distributing the negative 3 over y gives us this. Combining the like terms in the middle gives us this. Let's go ahead and put this back into the integral. So now we have this. I'm going to rewrite both of these two terms a little bit. Now we are ready to integrate term by term. Let's leave the pi out in the front outside of parentheses. The antiderivative of 25 is 25y. I'm going to just bring down my constant of negative 30. Now here is a memorized rule. The integral of 1 over y is the natural log of the absolute value of y. Considering that we are strictly in the first quadrant the entire time, the y values are definitely positive, so we don't actually need the absolute value. Moving on, I'm going to bring down my y for this third term. Increasing the exponent by 1 makes this the negative 1 power. And then dividing by the new exponent makes negative 9. So really, instead of putting plus, I will just put minus 9. Applying the limits of integration, we have 1 and 4, which means that we need to find the value at 4 minus the value at 1. On the next step, I think I will write this as 9 over y. So here's my pi still out in the front, and then I have the value at 4 minus the value at 1. We know that the natural log of 1 is 0, so on the next step, this term will be gone. I'm also going to distribute this negative sign and remove the brackets. So this will be a plus 9. So now we have this. 100 minus 25 plus 9 is 84, so we have this. Making like denominators gives us this. And subtracting these fractions gives us this. So this is the volume of the solid of revolution. However, if this was a free response question on an exam, I would recommend leaving your answer in this form so you don't lose points needlessly for a careless mistake made during the simplification process.